We've got a few minutes left, I guess, so why don't we talk about our paper. Oh, I give you the new one, right? This is some square wave voltammetry stuff, so we can think about square wave voltammetry next time. This is the old one. This is the one we're talking about. This one here, the extraction of copper and copper-2 ions. I thought this was interesting for a couple of reasons. One was the fact that it was really a non-metal electrical system. We don't have any. We have some electrodes in there, but they're not really involved directly in the electrochemical process. They're just involved in setting potentials of the interfaces. What's the electrochemistry going on? What's actually happening in this particular system?
Copper is, but it depends on what we got initially. If we have copper 1, it goes to copper 2, and then copper 2 goes into the organic phase, and then reducing the organic phase. That's
yeah, there's a transfer from, I guess the more fundamental thing, I guess, is there's a transfer from an ion and an aqueous phase, right? Copper 1 to the organic phase. And that's assisted by this ligand, this thioligand. Okay. What I thought was interesting, because do you understand the shapes of the, if you look at figure 2 and figure 3 and figure 4, now if you haven't done much electrochemistry before, you might not recognize those, but if you've done some electrochemistry, you see those look exactly like the curves that we're going to see next time for cyclic voltammograms. They're not particularly perfect looking waves, but they have the peaks like voltammograms do and so on. But these are not electron transfers. What's being transferred across the interface? And so what's the current that we're seeing? Is it the electrons being transported across the interface? Yeah, it's ion. So it's the current that you're seeing is an ion current, not an electron current. We're not moving electrons across the interface. What I thought was also as interesting was the units here, delta, and it's W over O phi. Where did we see phi before used as a number? When did we use phi as something? Yeah, it's the internal potential, right? It's the potential, the inner potential of the phase. So what they're saying is that they're looking at the inner potential phase differences between the water and the organic phase. That's not the same as what we normally use for metal electrodes. We just use a potential that's applied versus a reference. And so as we increase the difference in potential between the two phases, what's happening? It's saying that at some point there is an energy barrier for getting ions into the other phase. And if we increase the potential enough, there will be a driving force for those ions to go across the barrier. And just like a planar electrode, there is a diffusion and a depletion happening, and that's why you're seeing those peaks the same way. And notice from figure 3 and figure 2, what's the difference between those two curves besides the shape?
The biggest shift
Yeah.
to the more negative potential in figure 3
Right.
to the systems of the negative.
So they can actually, you see a shift when you put that ligand in, which makes it, they suggest that the ligand actually facilitates the transfer, makes the barrier less. And actually, they're using that information, if you look on equation 3, which is on the second page, 838. That shift, you can see there's the delta phi 1/2 is with a ligand associated with the metal is the equal to the shift, or what the value is with just the metal alone, plus a stoichiometric factor, which is that beta. That's how many metal and ligands get together to do the transfer. And then there's a ligand concentration here in the second part. So what you're saying is an equilibrium situation. As you change the equilibrium, the ligand and metal, the potential shifts as you make it. You can make it easier or harder to get that across as we add more and less ligands. And so this is an equilibrium process, no kinetics really in this particular situation. If you look in figure 3, you see that little squiggle there, again, that squiggly E. And again, it means the same as in this as it does for the other one. It's the mass transport. In this case, the water and organic phase have different diffusion coefficients, so they have to use that. That's actually very important in these cases, because often it's the case that the two different phases, the diffusion coefficients would be quite different. All right. And then the last half of the paper, they talked about the effect of copper being reduced by the ligand in the organic phase, or the salt, actually, the anion of the salt in the organic phase. All right. Any other comment? There's some more things we can talk about, but I know our taper wants to get out of here at 5, so yeah. So we better quit. So.